For decades, corporate IT operated under the myth of a weightless, infinite cloud. Generative AI has shattered that illusion, bleeding enterprise budgets dry one prompt at a time. The financial reckoning arrived when a major enterprise issued AI licenses to its workforce without limits. Unmonitored employees engaged in token maxing, resulting in a single-month invoice for $500 million. That $500 million bill came from mundane tasks. Employees used premium, compute-heavy reasoning models to do things as simple as checking the local weather forecast. Generative AI has broken the flat-rate software licensing model. It functions as a metered utility, where every prompt represents a variable transaction that consumes raw compute power. Falling token prices haven't lowered total costs. This is the Jevons paradox. As cognitive processing becomes cheaper, corporate demand for it expands exponentially, keeping total bills high. This crisis is accelerating as companies move towards autonomous agents. Unlike a standard chatbot that runs once, an autonomous agent operates in a continuous runtime loop. This chart shows the auto loop tax. To finish a task, an agent must reanalyze its entire interaction history at every step. A multi-agent system can consume 15 times the tokens of a standard prompt just to reach a successful state. Every uncontrolled agent loop places an infinite demand on a finite pool of physical hardware. To understand the cost of that demand, we have to look at the silicon layer and the core physics problem of AI, the von Neumann bottleneck. Traditional GPUs physically separate the computing processor from the data storage. To perform a calculation, the two units must communicate across a narrow physical pathway called a bus. Imagine a skilled chef working at a tiny cutting board. To read one line of a recipe or fetch an onion, the chef has to sprint down a mile-long hallway to a pantry, run back, and make one cut. Shifting data from memory to a processor consumes orders of magnitude more power than the actual math. The exorbitant heat and energy demands of AI data centers are driven by this microscopic commute. Instead of fixing this bottleneck, the industry is attempting to brute force the problem by building massive, hyper-dense data center clusters. Building these facilities requires a specialized workforce. The industry faces a critical shortage, needing roughly 500,000 new electricians to support the build-out of these hyperscale campuses. Compressed 24/7 construction schedules have introduced deadly physical hazards. In 2022, an electrical incident at a Google data center in Council Bluffs, Iowa, critically injured 3 workers. An arc flash occurred when electricity bypassed its path and superheated the air to 35,000 degrees Fahrenheit, 3 times hotter than the surface of the sun. This strain has led to the proposed AI Data Center Moratorium Act, which seeks to pause construction until regulators can secure grid safety and worker protections. Forcing an inefficient technology to scale at this speed creates a breaking point for local infrastructure and the labor force required to build it. Standard utility grids cannot handle the gigawatt demands of AI campuses. To bypass the grid, developers are installing their own fossil fuel power plants directly on site. In South Haven, Mississippi, Elon Musk's xAI facility demonstrates the scale of this expansion. It is a $20 billion complex situated directly next to a residential neighborhood. The developers installed 57 mobile, natural gas-fired combustion turbines right against the residential property lines. These turbines produce high-pitched squealing and low-frequency infrasound that physically vibrates neighborhood homes. Residents describe the constant industrial roar as an inescapable acoustic cage. The digital cloud has a tangible footprint. It raises local temperatures and alters the acoustic reality of the neighborhoods it occupies. The $500 million software bill, the sweating microchip, the electrical arc flash, and the roaring gas turbines are all linked. Moving data across a chip wastes so much energy that it creates a heat and power crisis the national grid cannot sustain. These events show what happens when we scale an architecture that is inherently inefficient. The gas turbines in Mississippi exist because our current chips are too power-hungry for the existing grid to support. Survival requires strict financial controls. Enterprises must adopt FinOps practices, implementing hard user spending limits and tracking the cost of every individual agent run. Companies must also practice grid awareness. AI deployments must account for the physical limits of the local power and water supplies they depend on. Finally, we need architectural efficiency. This is the traditional von Neumann architecture, where the bus creates the bottleneck. Solving this requires a move toward digital in-memory computing. Digital in-memory computing performs math exactly where the data is stored. By embedding compute into the memory itself, we eliminate the power-hungry data transfer and the bottleneck it creates. Treating AI as an infinite resource is no longer viable. Market dominance will belong to the organizations that master architectural efficiency and operational governance.